Okay, we are going to talk about linear programming today, which is 7.6. And linear programming is going to put together all the things that we've been working on in Chapter 7. So it goes back and it uses like our solving systems from 7.1 to 7.3. And then a big part of what we do in linear programming is from last night's homework, that great question that Callie asked us at the beginning, number 66, writing our own inequalities and graphing that region where the combined solution is located. So the main goal of linear programming is to optimize. And when you think about optimizing, you're thinking about finding the minimum and maximum in a certain situation. In order to do this, to find the min and max, we need to do like a little bit more than what we did yesterday. And one of the key pieces is you've got to find out what it is you're trying to minimize or maximize, and then you've got to write an equation for it. In linear programming, that has a special name. It's called objective quantities. So the objective quantity, and I often sometimes call it objective function, is really just an equation. For our word problems, you're often going to be working with profit and cost. So when I write the objective quantity, I often write P equals or C equals. You're going to see on our first two examples, it's not about profit or cost because they don't have any context. So then it's just written as a Z equals. It could really be any letter other than the X and Y variables that you're using. Okay. Now the next three parts of linear programming are the stuff we already know how to do from section 7.5. So set up constraints, that would be the question Callie's asking about in number 66. The graphing of the constraints, that would be the piece that we talked about yesterday where we find the combined solution for all the inequalities. And then also finding their vertex points. These things are coming to us from section 7.5. Now, the vertex points will be tested in your objective quantity. Remember, the objective quantity is just an equation, and you'll have XY ordered pairs for your vertex. You will plug them in, and you will just see which one produces the highest or the lowest value, and that's how you'll find minimum and maximum. So we are guaranteed in linear programming that the min or max will occur at a vertex of a bounded region. Okay, so the min or max will occur at the vertex of a bounded region. And then after you test those vertex points, all you have to do is like make your statement. Like, you should buy this many of this and that many of that. So like we could have done that for Callie's question number 66. If we graphed that system, we found the vertex points and we plugged them in. If we had an objective quantity, plug them in, see which ones gives us the max, and then choose those values of the computers to buy. Okay. So it's a very useful process. Now, if we were using linear programming in the real world to decide some things like where are we going to put our next McDonald's, or where are we going to send our troops for some particular mission, there might be a lot more variables than one person alone could work with. So the whole idea of programming lends itself to what? Computers, right? You might plug your equations into the computer and let the computer solve for the values that you want. Okay. Okay, so let's look at example number 1. Okay. It says, find the min and max values of z equals 3x plus 2y. This right here is your objective quantity. We'll come back to that at the end so that we can plug our vertices in and see which one provides minimum, maximum values. These inequalities that are already done for us, so we don't have to set them up, are our constraints. So they are our limitations to the problem. Okay, these things must be true of x and y. So we got to, on this problem, we got to skip over number 1. We didn't really have to write the objective function, and we didn't really have to set up the constraints. So we can go ahead and start with graphing. Okay. Now, I'm going to show you a method here momentarily that makes graphing things in standard form a little bit easier. Okay. But let's start by graphing x is greater than or equal to 0 and y is greater than or equal to 0. What type of line are we graphing for x is greater than or equal to 0? Vertical line. That is the y-axis, correct? So let's draw a solid line because it's or equals to on the y-axis. Since it says x is greater than or equal to, in which direction would you shade? Towards the positive axis, which would be to the right. I'm not going to shade it because I'm working in pen there, so I'm just going to make a little arrow pointing to the right so I remember I'm shading to the right. My y is greater than or equal to 0 is what type of line? The horizontal line. It is the x-axis, so I'm going to go ahead and draw a solid line on the x-axis. Since it's greater than or equal to that, I would be shading up. And I'm now restricted to which quadrant? First quadrant. Like the overlap of those two shadings is only in quadrant 1. Okay, so I want to keep track of where my combined shading is, because in the end I want just that works for all of them. Okay. Now, a lot of real world problems that we do will be restricted only to quadrant 1, right? It doesn't really make sense to go in the negatives for like how many models of something you're going to purchase, like in that number 66 we talked about. Okay, okay, now we're going to graph those other lines. And so I'm going to show you a method called the intercept method. I'm going to start with this constraint right here, x plus 2y is less than or equal to 4. And I'm actually going to think about it just as the equation of a line, x plus 2y equals 4. You can solve for y and make this look like slope-intercept form if you want to. But I've got this method where I can find x-intercepts and y-intercepts really quickly, and it makes it just a little bit faster to graph, which is helpful. So remember, all x-intercepts will have a y-coordinate of 0. All y-intercepts will have an x-coordinate of 0. So I'm going to start with just the x-intercept right here, and I'm going to plug 0 in for y. If you plug 0 in for y right there, what happens to 2 times 0? It's just 0, and x plus 0 is just x. So then I can, since 2y is going to be 0, I can cover that up, and what equation is left over? X equals 4. So the x-intercept is at 4. If I want to do the y-intercept, I plug 0 in for x, and that will make that kind of just go away, turn to 0, right? Identity property. And then I'm left with the equation positive 2y equals 4, so what's my y-intercept? 2, because you would solve that by dividing both sides by 2. So my y-intercept is at 2. Now I can plot those over on my graph. An x-intercept at 4, so I'm going to count 4 to the right. A y-intercept at 2, count 2 up. This is going to be a solid line. And that was pretty easy to graph. Now, to decide where to shade on this one, because it's not y is greater than or y is less than, I would use a test point. A really good, quick, easy test point for me would be 0, 0. So if you plug that into the inequality, 0 plus 2 times 0 is less than or equal to 4. True or false? True. So you want to shade where 0, 0 is. You're shading on this side of the line where is your combined solution now?
That little rectangle.
This little triangle right here, okay, is the combined solution if I'm keeping track of that. Okay. Let's graph that other line using our intercept method. If I plug 0 in for y, my x-intercept is at 1 because I just have x equals 1 left over. So I'll put an x-intercept at 1 to the right. If I plug 0 in for x, I'm left with the equation negative y equals 1, which means y is at negative 1. So I should go down 1 for the y-intercept. Are we okay with that intercept method? Yes. I also sometimes call it cover-up method because you're just covering up one of the variables and solving for the other. That's finding its intercept. This is also going to be a solid line. Decide where to shade. I could plug 0, 0 into this inequality. 0 minus 0 is less than or equal to 1. True or false? 0 minus 0 is less than 1. True. 0 is less than 1. So we should shade where 0, 0 is. You're shading above this line. And so now our combined shaded region is this little shape right here. How many sides does that shape have?
3.
4. It's very little, so it is hard to tell. Okay, zoom in right there. Okay. Now, that shape has a special name in linear programming. It's called the feasible region. Feasible meaning?
Possible.
Yeah, it's possible because it works for all. Okay, after you graph the constraints, if you look up at our little checklist at the top, then we need to find the vertex points. So if you're using a coordinate plane and you have used a straight edge and you have graphed very carefully, it might be possible for you to pick your vertex points off from the graph. So like, what are the corners of this little quadrilateral?
0, 0.
0, 0 is one of them.
0, 1.
0, 1?
I meant
1, 0, that x-intercept, right?
2, 1.
2 to the right and 1 up.
And then 2, 0.
2, 0.
Wait, no, 0, 2, sorry.
0, 2. Yes, y-intercept. Okay. So those are your vertices. If you have a maximum or minimum for the bounded region, it will occur at one of those vertices. So we just have to plug them into that objective quantity and see which one gives us the highest and the lowest values. So remember we had listed our objective quantity over here as z equals 3x plus 2y. So I'm going to say z equals 3 times 0 plus 2 times 0. That's 0. Then I'll try the next point. Z equals 3 times 1 plus 2 times 0. That's 3. So right now I have a minimum of 0 and a maximum of 3, but I got to keep checking. See if anybody's lower or higher. Z equals 3 times 2 plus 2 times 1. That's 6 plus 2, which is 8. So now I have a maximum of 8 and a minimum of 0. And the last one, z equals 3 times 0 plus 2 times 2, that's 4. So can you identify your final min and max? Yeah. Min at 0, 0. Max at 2, 1. And the minimum value is 0, the maximum value is 8. So, like, if we were going to make a decision about something, suppose that's kind of like Callie's question with the model computers from 66 from yesterday, then we'd say, for maximum profit, buy 2 of Model A and 1 of Model B, because that produces the maximum, if that were that example.
How would you do it if it was like just normal less than and not less than or equal to?
I don't know that I'll ever really give you one like that. I would say if one of your lines or curves was a dash curve, then that vertex wouldn't really count, right?
Yeah.
So I would find all the other vertices that were intersections of solid lines and leave that one out, because you can't really use that. It doesn't fit the constraints. Okay. Okay, let's try example 2 just really quickly. The reason why I have example 2, oh, and really important, cross off that last one. Woo, don't need that. You'll get no solution if you graph that one. Okay. The reason why I want to show example 2 is because for some of yours, if you use the intercept method, some of your intercepts are going to be at what I would call not nice numbers. Is that okay? Absolutely, we do not discriminate. Okay, remember we're equal opportunity for numbers. Okay, so let's start with that very first equation. Using your intercept method, what's your x-intercept?
Your x-intercept would be,
Courtney says 4. What is your y-intercept? John says 2. So we'll plot those. This is or equals to, so it'll be a solid line, so we're not going to run into Mason's issue of dashed lines that wouldn't be included. Maybe check my shading. Is 0 greater than 4? If I plug in 0, 0? No, so I should shade above this line. Okay, so I'm shading up. Okay, so what's your x-intercept for the next line?
7/3.
7/3. Is that okay? Yes. Where is 7/3 located?
this is 2 and 1/3.
2 and 1/3, so a little bit past 2, right? So if I'm going to do my x-intercept for 7/3, I'm going to go to my origin. I'm going to count 1, 2 to the right, and a little bit more. There's 1/3. No big deal. What is your y-intercept there?
7.
7. So we can count up 7. Graph that line. Think about shading. If you plug 0, 0 in for x and y, 0 is greater than 7. No, so do not shade where 0, 0 is. You'd be shading up from this line too. So now we're kind of restricted to this area right over here. Okay. Last one. What's your x-intercept?
-7.
-7. So we're going to go 7 to the left. And my y-intercept?
7/2.
7/2, which is
3.5.
3.5. No big deal. We'll go up 3.5. Cool. Draw my line. Now remember, if you would prefer to write those in slope-intercept form, y equals mx plus b, I'm totally okay with that. In terms of graphing, this is probably a little bit quicker to identify your intercepts. Okay, so it makes it a little less painful for some of us. Now, decide where to shade. If you plug 0, 0 into this inequality over here, you would get 0 is less than 7. How do you feel about that statement? Good. So you should shade where 0, 0 is on that line, which is down on this line. What line did I just grab? Oh, sorry, this line right here, right? down from this line, so that restricts us to everything right in this section right over here. Now, compare your feasible regions from example 1 to example 2. What is a big difference in your feasible regions? What do you notice as different between the two of those? Lillian?
It's like not a closed figure.
This is not closed, so this we can say is unbounded. It's not closed on all sides. Sorry, you can't see that I just wrote unbounded down there. The other one we would call bounded on all sides. Okay. What might that mean for your max and your min? If it's unbounded.
There isn't one.
You might not have a max and a min value, right? If I could plug like more and more numbers, like as I'm going into this section up here, think about plugging those into my objective quantity, which is right here, 4x plus 2y. If my x and y are continually growing, that's going towards positive infinity, right? And then over here, this is now going into like negative. Okay? So we're thinking that's probably also approaching a negative, because this could get more and more negative. So we might say there is no max or min. You like that?
Yeah.
Okay, are there any questions that can be answered? Okay, let's try a word problem. Let's go to the back. There is a typo in example 3. Do you see at the very end of the first sentence it says question mark $250? That is just $250. So if that bothers you, you can cross that off.
No, it doesn't have that.
It does it?
Oh, wait, no, it does.
Oh.
Yeah. You got so excited.
Well, I was like, that's weird because I made copies of mine from yours, so that was weird. But I did fix it later. Okay. These are the things over here that we need to do to be able to get our final answer. We need to figure out the objective quantity, so we're going to write our own equation for profit or cost. We need to write out the constraints. So this is like Callie's homework question. We are going to write the inequalities. We're going to have to graph them so that we can find the vertices, and then we'll just plug into our objective quantity to get our answer. Okay? So let's start with our objective quantity. Remember, that's what we're trying to minimize or maximize. Kind of scan that question. Are we minimizing or maximizing something here?
Maximize.
We are going to maximize the profit, right? So we want to write an objective quantity function that has to do with the profit of these, what are they, DVD players. Rescan your problem. Is there any information about profits in there?
Yeah.
Oh, yes.
Oops. What kinds of things do they tell me about profit? Do you say anything about profit, Dylan?
Yes.
What do you see? Well-
Yields a profit of $45, and the 400 vol yields a profit of $50.
Okay, so we want to use the numbers 45 and 50 in our objective equation, or our objective quantity. And what we would really like to do is then to write that in terms of x and y, so we better think about what are two things that could represent our variables for x and y. Lillian?
The $250 model and the $400 model.
Yeah, the $250 model and the $400 model. Thank you. So what kind of profit do you make for objective quantity on the $250 model? 45x. So if I sell one of those, I get $45. If I sell two of those, I get $90. If I sell 10 of those, I get $450. And what about for the $400 model?
$50.
50y. Not bad, right? Okay, now I want you to kind of scan through that problem. What are some limitations they're putting on you? What are they saying you can or cannot do?
They don't want to invest more than $70,000.
Okay, no more than $70,000. Is that going to be a greater than or a less than?
Less than.
Okay, we want something to be less than or equal to that $70,000 investment. And then how much would we be paying for the models?
205x plus
150x.
350y.
Well, I'm reading up in that very first sentence. This one's a little bit funny. At cost of $250. So I'm thinking about it like it costs them $250 to make that, and then it yields a profit of $45. So if we're thinking about like maybe the price that it's sold for, that's not necessarily its selling price, $250.
Also, would you add the profit cost?
No, well, no. So like, how much does it cost the company to make that first Model X? $250 at a cost of $250. So yeah, that one's a little bit funny.
It's weirdly worded.
Yes, it is weirdly worded. How about the other model? 400Y. I like your thought if we were told selling prices, and I see that like how you could think that that was a selling price. But if I go back to that for cost, I'm thinking those are the costs. Yes, sir.
You also have the constraint of like the x being greater than or equal to 0, same with y.
Oh, that's a good one. Real world constraints. We wouldn't tell them that they should buy -2 models. They'd kind of look at us funny. Okay, what does that mean?
They give us DVD players.
Are there any other constraints?
The DVD, the total monthly demand for the DVD players will not exceed $250 or 250 DVDs.
The demand for the DVDs is not going to go over 250. So it's going to be less than or equal to 250. And how can we write that in terms of X and Y?
X plus y is less than or equal to 250.
Yeah, all the models together, so X and Y must be less than or equal to 250. Okay, now here's the thing about drawing your own graph. Because of Mason's real-world restrictions, got to be greater than or equal to 0 on both the x and the y-axis, I'm going to be restricted to only the first quadrant. So when I draw my graph, I can draw a pretty nice-sized graph that is only the first quadrant for my x and my y. But I want to make the most of that graph on my paper. So what I'm going to do is I'm going to use my calculator, and I'm going to figure out what are my x and y intercepts for my constraints, so that helps me decide my scale. Okay, so I'm going to, in my calculator, oh, I already have it up. I would calculate that's my computer. Hang on. I would calculate the x-intercept, so 70,000 divided by 250, and the y-intercept, 70,000 divided by 400. So I can see on the x-axis I need to get to at least 300, on the y-axis at least 200, and then if I look at the second constraint, my intercepts are going to both be at 250. So now I'm thinking, like, let's just go 300 on both. And since I'm going that big, I'm going to scale by something, so like I'm not spending my entire time writing down tick marks. I'm going to scale by 50. Okay? And try to make your scale, your stuff evenly spaced. 50, 100, 150. Don't have to say all the numbers, but I could. And I'm going to do that on both axes. And I didn't do a very good job of spacing on my y. But then I can use those y-intercepts that I just found in my calculator, and I can use those to graph my two equations aside from x is greater than 0 and y is greater than 0. So I had one at 280. That was an x-intercept. I'm going to mark that because it's not on a nice number. And I also had one at 175 for my y-intercept, so I'm going to mark that just in case those happen to be my vertices, and I have them already labeled. I don't have to redo my math. And when I plug in 0, 0 on this one, 0 is less than 70,000, so it'd be shading in the triangle. The other line is going to have intercepts at 250 on the x and the y. And since those are on my nice points, I'm not going to label those intercepts. I'll be able to easily identify them if they happen to be vertices. And again, if I plug in 0, 0, 0 is less than 250, so I would shade below. And this is my feasible region right here. So I've got vertices at 0, 0, 0, 175, 250, 0, and then I've got this vertex right here, which to me looks like it might be at 200 and then 50, but I didn't graph on a nice piece of paper. So if I really want to make sure that I have the right location, I'm thinking these are the two lines right here. Set up a system. 250x plus 400y equals 70,000. X plus y equals 250. Solve the system. I could solve this by elimination. Times negative 250. That gives me negative 250x minus 250y equals negative 62,500. Stack my other equation below. Add to get 150y equals 7,500. If I divide, I find out that y is equal to 50. And I know I'm doing that math really quickly, but you're just looking at what are the equations of these two lines, write them as equations and solve the system, like we did in section 7.1.7.2. And if I know y is 50, then I can plug that in. X plus 50 equals 250. Sorry, you can't see that. And then x is equal to 200. So I did have the right location. You could write a note up here. This is solve the system. Now the bell's going to ring shortly, so I'll just say I'll take those numbers, I'll plug them into my objective quantity, and the one that gives me the maximum will be what I tell the company. You should get this many of each DVD. You have a homework assignment. Please work on it. There is also a 7-4 video that I will post later today. Please watch it. It is due on Tuesday, so if you have a busy Monday night, watch it this weekend and take your notes so you're ready for Tuesday.